electron deficient compounds and the expanded octet. Remember?
Yes.
So please keep your notebook and pen ready. Today we are going to learn about sigma bonds and pi bonds, how they are formed. Okay, so sigma bond, which is represented as this sigma, it is formed by the end-to-end overlapping of two orbitals. End-to-end overlapping, or you can say the sideways overlapping. Sorry, head-on overlapping. End-to-end overlapping or head-on overlapping of two orbitals. Which chemical bond is created is called the sigma bond. So let us see how sigma bond is created between ethane. So this is my C carbon orbital. Carbon have, this is C, and this is also carbon. Now H hydrogen is spherical, right? It has only one s orbital, so we are making it like spherical. These are my hydrogen orbitals, which is spherical in shape, and the p orbital of carbon is dumbbell in shape. Now what happened? This orbital of carbon and this orbital of carbon, when they overlap head-on or when they overlap end-to-end, then a bond is created which is known as your sigma bond. So in the figure you can see that these are my CH sigma bonds. Okay, for example, ethane will make like this, CH3 and CH3. So these are my CH sigma bonds, and this CC, it is my CC sigma bond. Okay, so one single bond contains a sigma bond only. Okay, and here also we have a sigma bond between carbon and carbon bond. So how sigma bond is formed? It is formed by end-to-end overlapping of two orbitals. Now there are various types of sigma bonds. Okay, there are various types of sigma bonds. One is your SS orbital overlap, next is your sp orbital overlap, and third is your pp orbital overlap. So this is my SS orbital overlap. S means it is spherical. It is also a sigma bond. When you have a overlap between p and s orbitals, this is my p and this is s, then also the bond which is created is called sigma. Third is our pp orbital overlap. This is also p and this is also p. When they overlap, then it is called a pp orbital. So it is also a sigma bond. Okay, so here you can see that here I am having an overlap of s orbital of hydrogen and p orbital of carbon, right? So it is a sp orbital overlapping, and sp orbital overlapping is called a sigma. Okay, so sigma bond is formed by the end-to-end or head-on overlapping of two orbitals SS, sp or pp. Is it clear?
Yes.
Write it down. You know, write down how sigma bond can be produced by SS orbital overlap, sp, and by pp. In the shape, you know, the shape of s orbital is spherical and the shape of p orbital is dumbbell shape. Next is our pi bond. Pi bond is formed by the sideways overlapping of two orbitals. Which chemical bond is created is called pi bond. For example, this is the p orbital, okay, and this is also the p orbital. Now, when the overlapping occurs between two lobes, this is my first lobe and this is second lobe. Similarly, this is first lobe and this is second lobe. Now, when the overlapping occurs between these two lobes, then that sideways overlapping is called pi bond. Okay, we represent it like this. And sigma bond, I hope the difference is clear. Sigma bond is formed like this by head-to-head overlapping. Okay, when only one lobe is interacting, then a sigma bond is formed. And when two lobes are interacting, then the pi bond is formed. So whenever we have a double bond C, then in this bonding, we have one sigma and one pi. If we have a C single bond, we have one sigma only. If we have C triple bond C, then in this we have two pi and one sigma. Okay?
Okay.
Right. Yes. So we have studied about the sigma bonds and pi bonds. So what do you think? Which is stronger, sigma bonds or pi bonds? So here sigma bonds are stronger. Sigma bonds are stronger as compared to pi bonds. Why? The reason is written here that carbon-carbon double bond, as I already told you that carbon-carbon double bond, it consists of one sigma bond and one pi bond. So it has a bond energy which is less than twice that of a CC single bond. Bond energy means the energy which is required to break 1 mole of bonds. Okay, so it has a bond energy which is less than twice that of a CC single bond. So which indicates that the stability added by the pi bond is less than the stability of a sigma bond. Sigma bond is more stable. From the perspective of quantum mechanics, this bond's weakness is explained by significantly less overlap between the component p orbitals. So, in your level, you can write this that pi bonds, sigma bonds are stronger as compared to pi bonds because of their overlapping. Sigma bonds overlap like this, and pi bonds overlap like this. Okay, so there is a less overlap between the component p orbitals due to their parallel orientation. They are parallel, right? So there is a less overlap between their p orbitals, and due to the less overlap, the bond is weaker. Which bond? Pi bond. So that's why your sigma bond is greater as compared to the pi bond. So you can write down this reason. There's a difference between sigma bond and pi bond, which you should know. First point is that it is formed by end-to-end overlap, sigma bond, and it is formed by sideways overlap, lateral overlap, sideways overlap, one and the same thing. Next, how sigma bond is formed? By SS orbital overlapping, sp orbital overlapping, and pp orbital overlapping. But in pi bond, you have the bonds where only pp orbitals overlap. Sigma bond is stronger as compared to pi bond. Number of sigma bonds present determines the molecular shape. When we study the hybridization, when we study the Vesper theory, we'll read that the molecular shape is determined only by the sigma bonds, not pi bonds. So it has no effect on shape. Free rotation is possible. Okay, carbon-carbon free rotation is possible. That means if there is a sigma bond, then you can easily rotate this bond. But if you have a pi bond, then free rotation is restricted. You cannot rotate this bond. This bond is not rotated because here is a pi bond, one sigma and one pi. So free rotation is not possible in case of pi bond. Okay, I hope these differences are clear.
Yes.
So this question is important first, that which bond is stronger, sigma or pi. So this is the answer and this is the reason, write it down. So basically pi bonds are weaker than sigma bonds due to the way they form, due to the overlapping. And you can write down the overlapping, that sigma bond is formed by head-on overlapping of atomic orbitals. So in head-on orbital, there's a stronger overlap, stronger bond. But pi bonds, they are formed by sideways overlapping. So it results in a weaker bond because the overlapping area is smaller. Okay, now write down the difference between sigma bond and pi bond. This is a very important question. Students generally do this mistake that pp orbital overlapping is pi bond. But no, not always. If pp orbital overlaps inside as a sideways, then it is called a pi bond. But if it overlaps head-on, then it is called a sigma bond.
Hey students! Interested in boosting your studies? Enroll now at Keddy Edtech. We offer online tuition for the Cambridge curriculum, grades 6 to IGCSE, AS, and A-level. Start learning with us today.
Now let us read about the bond length and bond energy. So we have single bond and double bond, right? If we have carbon-carbon single bond and carbon-carbon double bond. Now which bond length is greater? So always remember that carbon-carbon single bond, it is greater as compared to carbon-carbon double bond. Because double bonds are shorter than single bonds. Why? Because double bonds have a greater quantity of negative charge between the two atomic nuclei, right? Because a single bond contains how many electrons? 2 electrons. And a double bond contains how many electrons? 2 pair of electrons, that is 4 electrons. So double bond have a greater quantity of negative charge between the two atomic nuclei, and the greater force of attraction between the electrons and the nuclei, it pulls the atom closer together, as we have read this in atomic structure also. So this results in a stronger bond. So carbon-carbon double bond is stronger as compared to carbon-carbon single bond. So we measure the strength of a bond by its bond energy. What is bond energy? Energy needed to break 1 mole of a given covalent bond in the gaseous state. Why in the gaseous state? Because we have to make sure that it is free from any other interaction. So we take gaseous state. Distance from the nucleus of one atom to another, it depends on the two atoms forming the bond, and the internuclear distance between the two covalently bonded atoms is called the bond length. if I'm having the hydrogen atom and if I'm having another hydrogen atom. Okay, they are covalently bonded. Now the internuclear distance between the nuclei of two covalently bonded atoms is called its bond length. Is it clear what is bond length and bond energy?
Yes.
Write it down. So you should know what is bond length. Bond length is the internuclear distance. Internuclear means between the nucleus of two atoms. Between the nucleus of two covalently bonded atoms. It's called its bond length. What is bond energy? Energy needed to break one mole of given covalent bond in gaseous state is bond energy. You should know which have a greater bond length. CC single bond or CC double bond. So CC single bond have a greater bond length as compared to CC double bond. Double bonds are shorter. Why they are shorter? Because they have higher quantity of negative charge between them, because single bond consists of 2 electrons only and carbon-carbon double bond consists of 4 electrons. So this greater force of attraction between the electrons and nuclei pulls the atom closer together, and if it pulls the atom closer together, it results in a stronger bond, okay, and its bond length will decrease. Okay, so bond energy is inversely proportional to bond length. It means that if double bonds have higher bond energy, then they are shorter. Okay, they have lesser bond length. Write it down. Okay, now look at the values here. Carbon-carbon single bond, it have a bond energy of 350. Carbon-carbon double bond, it have a bond energy of 610. But as I told you that bond energy is inversely proportional to bond length. Okay, so that means that here bond energy is increasing, but here you can see bond length is decreasing. Okay, carbon single bond O, its bond energy is 360, but carbon double bond O, its bond energy increases to 740 kilojoules per mole. But see, look at the bond length. Here, carbon oxygen bond length is 0.143. Its bond energy increases, so its bond length will decreases, and it is in nanometers value. Okay, so this is your homework question. You can take a screenshot of a homework question that the table lists bond lengths and bond energies of some hydrogen halides. Okay, hydrogen chloride, hydrogen bromide, hydrogen iodide. Bond length is given in nanometer. Nanometer means 10 raised to the power minus 9 meters. Bond energy is given to you. You have to answer only 3 questions, which are very easy if you understood the bond length and bond energy concept. Question number 1 is describe the relationship between the bond length and bond energy. As I already told you, they are inversely proportional. Suggest why the bond energy value decreases in the order and suggest a value for bond length in hydrogen fluoride. Okay, so you can compare it from the hydrogen chloride, bromide, and iodide, and you have to suggest a value for the bond length in H. Is it clear?
Yes.
Any doubts till now?
No.
Now the next concept we'll read this in chemical bonding, which is very important from examination point of view. That is Vesper theory. Vesper theory is valence, shell, electron, pair, repulsion theory. What does this theory state? It states that because all the electrons have the same negative charge, obviously they repel each other when they are close together. When two negative charges are close together, they will repel. So pair of electrons in the bond surrounding the central atom in a molecule, it will repel the other electron pairs, and we have to minimize this repulsion. So this repulsion forces the pair of electrons apart until the repulsive forces are minimized. So the shape, basically this theory tells us about the shape and bond angle of your covalently bonded molecules. This is not for ionic molecules, only for covalently bonded molecules. It depends on the number of pairs of electrons around each atom, whether these pairs are lone pairs. Okay, we have already studied about lone pairs. They are unshared pair of electrons, or bond pairs, which are shared pair of electrons. So from this theory, we'll tell the shapes and the bond angle and the geometry of your covalently bonded molecules. We place the atoms in such a way that the electron repulsions are minimized. So this is the key concept of the Vesper theory. So the valence shell electrons are the electrons in the main outer shell. Okay, for example, for sodium, its electronic configuration would be 2, 8, 1. So 1 is the valence electron for sodium, which are present in the main outer shell. Pairs of electrons repel each other because they have the same charge. Okay, if we have two negative charges close together, they will repel each other. A lone pair of electrons repel each other more than a bonded pair of electrons. That means if you see the degree of repulsion, then lone pair repulsion is greater as compared to lone pair, and the bond pair repulsion is minimum. Repulsion between multiple and single bonds, it is treated the same as for repulsion between the single bonds. Okay, repulsion between pairs of double bonds are greater. Shape of, because why it is greater? Because they have a greater quantity of negative charge in double bonds. Shape of a molecule, it can be deduced using this theory. Okay, so from this theory we'll tell the shape of the molecule, and the most stable shape is that which minimizes these force of repulsion. So these are the basic postulates of Vesper theory. Okay, you want to write it down? Write it down. These are the postulates. You can see here this diagram. This is a diagram for water, H2O. So this is the order of repulsion. Lone pair repulsion is greater than lone pair, and bond pair. So H2O, it is like this. Okay, oxygen have two lone pairs. Why? Because oxygen atomic electronic configuration is 2,6. So one electron is this, which is shared with hydrogen. One electron is this, okay, which is shared with this hydrogen too. And we have 3, 4 as lone pair, 5, 6 as lone pair. So we have two lone pairs of electrons on the oxygen. Now see, greatest repulsion between the lone pairs, intermediate repulsion between the lone pair and the bond pair, and the least repulsion between the bond pairs. And the bond angle for water is 104.5 degrees. Okay. So this is important. Draw this. Bond angle for water, you should remember it is 104.5 degrees.